Welcome to Third Angle, where we put the strength of American football helmets to the test. I'm your host, Paul Hames from industrial software company PTC. In this podcast, we share the moments where digital transforms physical and meet the brilliant minds behind some of the most innovative products around the world, each powered by PTC technology. American football players have to deal with a lot during their careers. Some of the hardest tackles they'll face will feel like being hit by a baby whale. So as thousands of pounds of force slam into them, athletes need to be prepared and protected. And a big part of that protection comes down to what's on their head. Now, you may look at a football helmet and think that it's no different to any other helmet, but the amount of technology under the hood will blow you away. The engineering that goes into a Xenith helmet in particular is second to none. Xenith is a company dedicated to safety, pioneering brand new ways to keep athletes safe on the field, supported by PTC partner PDS Vision. Our producer, Bryce Huffman, went to Xenith's headquarters in Detroit, Michigan, to meet their chief engineer, Ron Jadischke.
So Xenith was founded in 2006 by a Harvard quarterback. He was an MD from Columbia University. The genesis of Xenith was basically, there's got to be a better way. The first helmet that Xenith ever developed was known as the X1 helmet. So Xenith's technology really focuses on fit. The X1 helmet has what we refer to as an adaptive fit technology. So there was a cable in the X1 helmet that was attached to the lower chin strap. And when you cinched down on the chin strap, it would tighten the cable around the head to give you a nice kind of firm fit around your head. The other piece of the component that Xenith had was basically these adjustable comfort pads. So the adaptive fit technology is really something that sets Xenith aside from the competition. The other big kind of differentiator is this concept of decoupling the head or decoupling the padding from the shell. The way that Xenith's technology works is it has this shock matrix, is what we refer to it as, which has these pods that are connected to a floating plate on the inside. And that's only connected to the shell in a couple of different locations. So when an impact happens, the impact will happen with the shell, but the padding is connected to your head. So the shell has this ability to move in a decoupled manner relative to the padding and relative to your head. And that's kind of the genesis behind the Xenith technology. The shock absorbers is another part of kind of Xenith's technology. The shock absorbers have this small hole in them. So it's a sealed system that has air on the inside. And it'll perform kind of one stiffness when it's under a lower speed impact. But when you have air in a pressurized cylinder, if you try to push it out really fast, it becomes harder to push that air out, so it stiffens the shock pod. So that's this stiffening effect, so you can perform better on high-speed impacts and also well on low-speed impacts at the same time. That's a really big part of the challenge in protective equipment, is to being able to protect against low speed and high speed. So right now we're in the Xenith test lab. We have a few different pieces of impact test equipment that I'll kind of talk you through right now. Here we have a couple of drop towers that we use on a regular basis, and basically this is that part of the ongoing quality control testing that we would do, and even developmental testing. Basically, the way the drop test happens is there's a head form that gets mounted to this carriage here. This particular one is a head form that would kind of represent like an average adult male. So that head form is mounted to this carriage. We connect the drop tower mechanism to the carriage, and this is all kind of pneumatically controlled right now. Once the drop tower is connected to the carriage, then we'll bring the drop tower and the head form up to its height. And once it's reached its height, which dictates the speed that it's going to fall at, we'll let go of the carriage and it falls down and impacts the flat pad below. So that would have been simulating basically the highest speed drop test that we would do. It's about 18 feet per second, which is a pretty severe impact. I think roughly 5.5 meters per second to do the conversion. That depending on the helmet, can generate, on a helmeted head form, Gs of over 100 Gs, potentially. Our real pass-fail criteria is a different metric than Gs. It's called severity index, and that's a injury biomechanics metric that really originated right here in Detroit at Wayne State University. There has been a pretty steady conversation about the health of the athletes. There's always a focus on player health as far as like head injuries and concussion goes, and a lot of the changes I've seen along the way have really been driven from the top down, really from the NFL level, as well as what the NFL has done through their ranking system to really drive high performance helmets to be out on the field. So I think in the future, there's just going to be this drive for more high performance materials, integrating those high performance materials more tightly, incorporating engineering into the development process, and being as efficient with your protection or your equipment development as possible. I think probably the biggest pinch yourself moment that I've had, and probably several members of the group here at Xenith, was really being part of this NFL Helmet Challenge. It began really back in the fall of 2019. It was a global challenge that was put out by the NFL and NFLPA under their Head Health Tech Challenge protocol to develop a game-changing helmet. So we thought, why wouldn't we compete? Why wouldn't we be a part of this? Because this is what we're here to do, right? Change the game. So we put through some proposals to be a part of that challenge, and were successful and competed in that challenge it was about a 2-year program. I think it was just a great experience for everyone here involved, as well as the partners that we worked with, and definitely paints a bright future for the products down the road. Yeah, so the other piece of impact testing that we do, and this is part of, again, that NOXI standard. This is known as like the linear impact test or the pneumatic ram impact test. And that pneumatic ram gets propelled at different speeds. So this particular one we're going to do is probably around 5 meters per second or 6 meters per second. The system's capable of going all the way up to like 10 meters per second, which would be able to simulate those super elite professional athletes. So that ram gets projected at this stationary head form, and you'll see that the head and neck will move and then pull the table along with it. Yeah, and it's a pretty big impact, you'll see when we run it.
All right, I'm going to just go ahead and let it rip. Oh, shoot.
The next kind of series of helmets was the X2 helmet, which came out in about 2011. Really, there were some upgrades to the technology there. And then right around 2014, we came out with the X2E and the Epic. And these are the two shells, or two different helmet models that you'll see here. The big step we took forward with the Epic is we introduced something new, which is called the multi-stage shock. So we refer to the initial shock design, I guess, as a dual-stage shock, which means that it's, kind of like a pod, essentially. That's the single stage. The second stage is that pneumatic effect that I explained. And then the third stage of this multi-stage shock is that center section of the shock, which can kind of rotate and shear in different directions upon impact, just to basically improve that rotational effect. And with X2E, we also added in different shock heights as well, really to kind of bolster performance in different impact locations.
Was this one actually worn by a University of Miami player?
Well, it may not have been worn, but it is autographed by a university. Yeah, it looks like it's Ray Lewis. Yep.
I'm for sure taking a picture of this. So this would have been obviously after Ray Lewis was not in college anymore. What would be like the main difference between this helmet and your newest models?
We've since kind of sunset the Epic helmet, and we have the X2E Plus in our model lineup. We have the Shadow, and we have the Shadow XR. The X2E Plus, I mean, we kind of refer to it as our workhorse, I guess. It has more of that traditional look, still uses that kind of legacy Xenith technology, In 2019, we introduced the Xenith Shadow helmet. We've got a little more kind of streamlined look to it. You can see with the center kind of mohawk region, a little more aggressive look, a little more aggressive feel compared to our more traditional X2E. The Shadow shell is it's moving away from that traditional hard plastic shell, and it's kind of like a quasi flexible shell. This particular helmet right here is flexible compared to if you were to pick up something like this guy right here. It's a little tougher. Yeah, so that is the Xenith Shadow helmet, which is still available. It's on the NFL rankings. It's within the green section on the NFL rankings, which means it's kind of a recommended helmet. And then this here is our kind of newest helmet model. This is called our Shadow XR. So this is really an evolution of what I was talking about earlier as far as the shock technology goes. Kind of the Xenith pods allowed us to have a geometry effect and a pneumatic effect to the shocks, but you get to a certain level where there's maybe other ways to approach it, and that's really what we did with the Shadow XR helmet. The Shadow XR helmet, we spent a lot of time kind of developing the geometries that were used in here, and basically what we were trying to focus on was a linear impact performance to basically reduce those G-forces, and then a rotational impact performance, which is really to reduce the rotational forces. So the Shadow XR, and this is kind of where we landed. We have these like castle-style geometries that can perform stiff in a linear impact, but they can also shear very easily for a rotational impact, just kind of amplifying that effect of this floating shock bonnet within the helmet shell. The other differentiator here, though, with Shadow XR is the material that we're using. The material we're using is highly kind of rate dependent, so it's quite soft to touch and feel, which is a nice feel like if you're putting the helmet on your head, or it also performs well if you for those like thousands of impacts that a player might see on the season or on the field in a season. But it also, the material itself has the chemical properties that it can like stiffen up and perform kind of like a Play-Doh or a plasticine, where it really rigidifies or stiffens upon impact, and that gets you the highest level impact performance. So for those 1 in 1,000 type hits.
So like if Ray Lewis was just running full speed at some point.
Yeah.
That was Ron Jadischke. Now, Xenith is renowned for being uncompromising when it comes to its sports protective gear's design, fit, feel, and performance. And for that, they use Creo. Now it's time to meet our expert, Brian Thompson, who heads up PTC's CAD division. Now, Brian, because of the organic shape of the helmets, a lot of the development of the shell takes careful surfacing work. So could you start by explaining Creo's surfacing tools and also what role they play in the design process at Xenith itself?
Yeah, sure. It's really interesting because we've seen an evolution of surfacing technology in Creo over the past decade, and there's been increased pressure on making really, really nicely, finely controlled organic surfaces on the exterior of, say, customer visible surfaces on the exterior of components in the electronics market, in automotive market, in aerospace and defense, and now in markets like the one that Xenith performs in. And so with Creo, you have really fine control over surfaces by building out curves, controlling how those curves create the flow of surfaces, controlling how different surfaces meet the continuity that you want at those connection points is totally controllable in Creo. So you can build surfaces from the ground up inside Creo with excellent fine control that make really, really beautiful flow lines for the eye to meet. It's really powerful. But there's also been quite a bit of evolution of what we call like free-form surfacing development in Creo as well, where you start out with a fairly bulbous shape and you push and pull on a control mesh. And we do all the underlying surface connective controls for you, but you can very rapidly build out something that gets very close to a final shape that you might want. We're finding more and more customers are using this free-form surfacing approach to do early prototyping, but realizing the surfaces are so good that they might actually bring them into production. But you know what? The different techniques are wildly different. It's in some respects a bit of trading control for speed. And it's really up to the user to decide how they want to proceed and what surface technologies they want. We're finding them being even mixed more and more in the same designs in sort of recent years.
Thanks, Brian. Really interesting explanation on the surfacing tools and also the flexibility that they provide as well at Xenith. Now, the other area that I think we want to touch on today is around the use of advanced assembly extension at Xenith, because Xenith themselves are doing some quite interesting things there. Could you explain to the listeners a little bit about what they're doing at Xenith with AAX?
Yeah, well, it's a great segue to talk about different surfacing and modeling approaches and then talk about advanced assembly capabilities in Creo, because oftentimes advanced assembly capabilities are thought of as a way to manage very, very large assemblies and contributions from, say, multiple design contributors across a very large dispersed team. And that's all true. But in the case of Xenith, you could see a scenario where you have wildly different modeling techniques being brought together in a single design, managed at well-known interfaces, where you might have, say, the energy absorption part of the helmet have very, very different modeling techniques and approaches than the outer surfaces, like we just discussed, which have very, very finely controlled parametric surfaces. And so something like advanced assembly can allow you to manage the interfaces amongst different parts of the helmet that have very, very different geometric modeling approaches because they serve very, very different purposes. And those could very well be contributed by different design engineers that are, have specific skill sets to deliver the capabilities that those surfaces that they need to design have to deliver. So in this case, it's really about managing the contributions of multiple engineers working in really the same model that have very, very different modeling approaches. It's not like a big dispersed team, but still a valuable way of controlling the design.
Thanks to Brian and to Ron for showing us around Xenith's headquarters. Please rate, review, and subscribe to our bi-weekly Third Angle episodes wherever you listen to your podcasts, and follow PTC on LinkedIn and Twitter for future episodes. This is an 1860 production for PTC. Executive producer is Jackie Cook. Sound design and editing by Ollie Guiu. Recording by Bryce Huffman. And music by Rowan Bishop.